I'll be recording this tutorial on reinforce, which is a policy gradient method used in reinforcement learning, and it's actually not a actor critic method. It's a method which only uses a policy network in order to make decisions in a markup decision process, and in order to try and maximize expected return, which is the objective. So I have the import statements here, which are what we're going to have to use in order to have like the libraries. So we have system, torch, gym, numpy, neural network from torch, optimizer, which will be used by atom optimizer function, functional, I need to double check what that's used for. This one as well, I don't know really what it's used for, and then pyplot. So yes, this was actually inspired by Christopher Yoon's Medium post. So some of the things I'm still not sure yet what they actually do, but I still wanted to record the video because if I just keep on trying to learn every single segment of the code, I'll never actually finish. So the first step that we're going to execute here is initializing our gamma. Actually, let's not do that. Let's first make our policy network class. So this will basically be the softmax function that will take decisions, and we will use it in order to basically train our policy network. And I forgot that this needs to be lowercase. Yeah. So it has an init method, and the init method will have the inputs. So this will be the inputs to the neural network. It's basically, for our case, in cartpole, where the inputs is the velocity of x, and actually no, I think it's a 4, an array of 4. I'm not sure in fact, but either way, that will be the number of inputs that is accepted by our neural network, and then the number of actions is also another argument that we're going to use. This is the size of the hidden layers, so the number of nodes, and I'll just say LR is the learning rate. So that the first thing we're going to do is we're going to call the superclass of the policy network in order to initialize it. So basically, the parent network of policy network is nn.module, since that is what's inheriting. So we're going to call the init method of that class, and I'm not entirely sure actually why this is necessary, but in all the tutorials it's required. So we call the super network of we call the init method of the parent network of policy network, and then we'll quickly just instantiate some of these arguments as member variables, and that's it. We just need to make the layers now of the neural network. So I guess we're using the linear kind of, I don't even know what you call that, like a linear layer in the neural network library, and I usually use Keras, so I'm not entirely sure if this is a fully connected layer. I'm assuming it is. I think it's the same convention, but it's just called a linear layer in Torch, because yeah, I usually call these fully connected layers in Keras, but I'm not going to like be 100% certain on that because I could be mistaken. So I just wrote this, and I'll explain it really quickly. So the first linear kind of layer will have input nodes size, and then the actual size of the network will be this. And since this is the output of this layer, the input of the next layer has to be the same. So it'll also have this many nodes, and then it will output the number of actions. Since there's only 2 in the case of cartpole, you move right or left, but we're going to actually do something weird with the softmax function and the forward function. So you'll see that in a second. But first, we're going to also kind of initialize the atom optimizer, which is used for the loss function. So it's like similar to gradient descent backwards propagation, but it has some optimization. That's all I really know. I don't know much else about it. And that's everything for this function. So I'm just going to scroll through because I'm not actually doing this off of my head. I have really not that good of an intuition yet in reinforcement learning to be able to do that. So I'm reading off of another screen. And what we're doing here in the forward pass at least is quite simple. We're passing the state through the through the neural network in order to get our estimate, and that's going to be used whenever we want to obtain a prediction of which action to take. So the first layer is passed through, and the activation function is the rectified linear unit, and then since once more it's a policy network, the next function actually uses a softmax activation function. So we get the two actions as outputs, but then the activation function gives it into a probability distribution that sums up to 1. So there you have it. And apparently dimension equals 1 is required here. Yeah, you can look up why that is. I don't know. Maybe I'll try to find why that is later, but unfortunately in the moment that is unknown. Sorry, I always forget the spacing that's required. And then this next method, as you can tell by the title, is going to give an action given a state. So the first thing we're going to do is manipulate the input, which is just a state, and it's a actual NumPy array. But in order for the function to work in the context of torch, we need to convert it to a torch. And we're going to first, before we convert it to a torch, do this, which is a squeeze, and unsqueeze, sorry, not squeeze, which will just add an extra dimension, because what we're doing here is making it two-dimensional, and because kind of torch does batch training, we need to trick it into thinking that there's a batch of states being inputted even though it's only one. So this is of course not efficient, so you should definitely try to modify this algorithm, I guess, to do the training in batches. But the issue with that too is, since the policy is fixed over each episode, if you do many episodes while keeping the policy fixed, you're kind of wasting training, because you should be updating the policy as often as possible in order to try to improve it. Of course, that's why temporal difference learning is so effective, even though this is actually a offline algorithm. But that's kind of why we have to do it. I guess I just answered one question. So you shouldn't try to do batch training, because then your policy will learn at a much slower rate, since you will have to hold it fixed over the entire training iteration, over the entire batch, sorry. So if you do 10 episodes in a batch, then for 10 episodes you can't touch the policy. But anyways, so now we're going to pass the state through into the forward function, and this is where that variable thing comes into play. I don't know what it actually does. Must do some type of normalization, I guess. Not normalization, but some type of modification of the input in order to make it suitable for the function. And then now that we have the probability, we're going to call the random.choice, which is just from the NumPy library. And this is why we have the self.numberActions as a member variable. And I see that I did that wrong, so there you go. And then we're going to define a probability distribution, which is following the following. So first, or the last function that we apply to a distribution is squeeze, to remove the unnecessary dimension that we added at the beginning. And then we have the probs, of course, since it's probability. Detach, which decouples this probability from the TensorFlow, the torch autograph kind of mechanism, which basically allows the gradients to be computed in a much more efficient way. But because of that, it's kind of connected to the system, which is a really bad explanation, but that's kind of what my understanding is. And basically we have to disconnect it in order to perform this operation, or else we might mess up things in the background. And then we're going to convert it to a NumPy, which is why this is np.squeeze, not the torch version, because we're basically removing the last dimension, with like the dimension of length 1 from the NumPy array. And then, yeah, that's the last thing we have to do is basically get the log probability, because this is going to be used in order to, this is going to be used in order to, how did I say it? In order to compute the policy gradient, we're going to multiply the log probability by the unbiased estimate of the return at that time step, which which is used for the policy gradient. So we need to compute the log probability of whatever probability the action, the policy network gave, and yeah. So we want more squeeze because we don't want the extra dimension, and then we actually index the action because it's the action that we took that we are specifically, how do I say it? Specifically interested in. So yeah, that's kind of it for this one right here. And then we're going to make a new column in the code, which will be the update policy function. So that's it for policy network. Update policy is going to work as following. It's going to take in as parameter the policy network an array of rewards, and also the log probabilities that we returned in the other function that we just made. And yeah, so that's it for the parameters. The first thing we're going to do is instantiate an array of discounted rewards and make it an empty list. And we're going to actually calculate these discounted rewards. So you need the GFT, which stands for this discounted reward from time t up to infinity or until termination. And then we're going to do the following kind of trick, I guess. So we're going to start at the length of rewards -1, because we're going to go in backwards direction. Boom. And then we're going to stop at -1. So basically we're iterating from the length -1 to 0. And this is in order to take advantage of the recursive nature of g of t, because g of t can equivalently be written as g of t times. So here's where we're going to have gamma, because we need that. Gamma times g of t plus rewards t. So there you have it. And that's it. We just need to know. Oh, I forgot we need to actually insert it into discounted rewards. So we're actually going to use the insert method instead of the append in Python, because we want to basically put the list in the correct order, but as it's currently done, we're computing it in the reverse order. So if we keep on inserting into position 0, we'll effectively reverse the list of the reverse order of the list, which is desired. I'm not sure what the time complexity is of doing append and then reversing at the very end versus inserting at position 0 throughout the entire loop. But in the worst case, I believe that it would just be as bad as reverse. So I think either method is valid, or there isn't an advantage of one or the other, but I could be mistaken. So we're going to now make discounted rewards the same thing as it was, except a torch tensor, since we're going to do some PyTorch manipulations, I guess. I'm not sure why it's not giving me the autocomplete. It's kind of annoying because I enjoy that feature. Just something that I want to say. Okay. So now we're going to go policy gradient as a empty list, and this is basically the all of the policy gradients for each time step that we're going to go ahead and compute. And in order to do that, we're going to go for log underscore probability, comma, g of t in zip of log underscore probs, comma, discounted rewards. What this is going to do is basically make an iterable object of tuples, and the benefit of that is that since we want to go ahead and compute the policy gradient for each one, which is the product of the two terms in the for statement, we can just go like this, log prob times gt, don't forget the negative sign, which I'll explain in a second, but instead of kind of doing log prob I times gti, we can actually combine them in a zip and basically do it in a more Pythonic way, compute the product. And the reason why we do negative log prob is because, as it's stated, if we tried to perform the policy gradient on the log prob times gt, that is essentially telling you how to maximize the expected return, which requires gradient ascent. But since Torch, or like the algorithm I used, was using the loss as gradient descent, gradient ascent is possible to do. You just have to move in the direction of steepest ascent. But for whatever reason, maybe it's easier to just do, or it's default gradient descent. You basically, instead of maximizing the expected return, you minimize the negative of the expected return, which is equivalent. So that's it. And then we're going to do something here, which is policy network dot optimizer dot zero grad, which will just essentially initialize all the gradients to be 0, because after like using it multiple times, I guess the gradients will not reset themselves, so you need to reinitialize it to 0. That's kind of, and since it's kind of a recursive process in the chain row, you're computing gradients based on other gradients. You don't want there to be some trace values that affect the rest. And then next, we're going to go ahead and change the policy gradient to be a stack. So it just basically concatenates all of the different policy gradients into one big array, but they still conserve their individual value. So it would just be a list of policy gradients. And the weird thing that's happening next is that we're actually going to sum over all of these, which kind of doesn't make any sense to me, but that's just how it is in the algorithm on the official PyTorch tutorial. So if anybody knows why that is, please tell me why. But it doesn't make sense to me. Of course, since the policy gradients are like around 0, it will like sum up to something that's not out of control. But it seems that you're just losing information when you do that. So I don't really get it. Yeah, I'm kind of realizing as I do this tutorial that I have many holes in my knowledge of this algorithm. So I need to get on that, but it's okay, since I want to get this video done in order to identify those problems. So the last things that I have here is the backward pass, which basically calculates the, what does it calculate? It calculates the backward pass calculates the gradients with respect to the policy gradient. So basically it's telling you in what direction you should move each weight parameter in order to minimize the objective. And then the optimizer step is what actually changes the components of the parameterized weight vector, or the parameters of the model, which in this case is of course a neural network. And yeah, that's it. So like the last function that's remaining, as you may guess, is main function, or I'll just do if think I did it in the wrong way. I always do it in the wrong way. Just goes to show that still a lot of work remaining to do. But yeah, it's supposed to be like this. I guess. Okay. So now we're gonna do make the environment, which is going to be carpool. If I didn't reference it already, which I already did, so it's okay. Then we're going to have the policy network, which we have to initialize. And this one is kind of annoying, so let's do it as quick as possible. So the size of the observation vector is observation space dot shape 0 in OpenAI Gym. The action space is a bit simpler. Not sure why the saving is failing, but that's okay. Action space dot n, so just the number of actions you can take in the action space. And then the hidden size is just whatever you want. In Christopher Yoon's tutorial, he did 128, and that's the discount factor. Sorry, the learning rate, not the discount factor. So that's how fast the gradient ascent, or like how fast the optimizer will modify the components of the weight vector. So episodes, we can like just do like 5,000, I guess, or let's just do 500. It doesn't really matter. Depends how long you want to train. Cumulative rewards. It's going to be the rewards reach over time. And then we're also going to do this one, which I just called S10S, which is basically the average over the last 10 episodes of cumulative rewards. So it gives the average reward. And then we're going to keep on going and finally enter the episode loop. So for episodes and episodes, can't spell, still can't spell, episode. We obviously need to get the state via resetting the environment. We'll initialize the log probability list and the rewards list, which we both want to track in order to use in the policy update method. And we're going to say that done is false at the beginning, since the episode is not ended, since it hasn't started yet. So while I'm not done, we're going to do the following. Action dot log underscore probability equals policy underscore net dot get underscore action state. So basically just calling the action, and we're also getting the log probability of that action, because that's going to be used for the policy gradient. And we're immediately going to append that to the log prob list. And what's next, guys? So now we're going to actually take the action in the environment. So I just like to call it S prime as like S prime, the next state, and then done, which tells us whether or not we're done, and then info, which gives some information which is not actually relevant in the context of solving the reinforcement learning problem. And then we're going to take this step in the environment with the action. We're going to immediately append rewards to rewards. And then, of course, since you don't want to be training on the same state, and you actually want to mimic the fact that the invasion moves through the environment, you need to update the state to what it is. Okay, so then after this, what we have basically is the update policy. So it's after each episode. We're going to proceed with that. How did I write update policy? Oh, it's with underscore. No. Sorry about that. So then update policy occurs with the policy net, which is the policy network, the rewards list, and the log probabilities, since those are the two components of the, what are those? Those are the two components of the policy gradient. And then now we're going to kind of just update our like our tracking lists, or like the lists which have the quantitative data in them. So for example, we're just going to go cumulative rewards dot append sum of rewards, and then I already have it written down here, last 10 episodes dot append np dot mean of cumulative rewards, and we always want to do the last 10 episodes. So you're going to go last 10 up to the very end, and then every single time we're going to print the following statement, which is notably the episode equals this. And I forgot this is going to be f string. What did I call it? I think I called it episode. Indeed. And I just realized that in the update function, I need to also input the discount factor, right? Right, the gamma. Okay, that's all looking good. And then total reward over that same episode is going to be, of course, equal to cumulative rewards. And then average rewards over last 10 is going to be equal to last 10 eps. And I might as well say last 10 episodes. And I believe that's it. We of course want to plot those, but that's actually not going to happen in this video since the training will take too long. But if you did want to plot it, all you would have to do is go like this. So you go plt dot plot of cumulative rewards. So this one will be a lot noisier than last 10 episodes, as you can imagine, since it's the reward over each episode. And since vanilla reinforce is a very unstable algorithm, you really need to use higher complexity actor-critic methods if you want to achieve state-of-the-art performance. This one is going to often perform poorly, but as it trains, the general direction or the general trend will inextricably, or rather without a doubt, be in the ascending direction. But once more, if you take the average, then you essentially soften all of the noise, and it will be much less variable. There will be less variance in essence. So I just wanted to point that out. If you want to have a graph that is essentially having less variance, then only plot the last 10 episodes. And then I'm just gonna give these some labels. So this is episode number, and then this one is going to be the reward, if I'm not mistaken, or you can say time spent uprate, since this is in the context of what is in the context of everybody. Card pull. Okay, so saving has failed, which is slightly concerning, but I'm going to try to run this and go through any errors if they present themselves, but I hope not. So let me just try to save. First of all, the notebook has been changed. I would like to overwrite yes. So let's just wait for this. Okay, I'll change the save. I'll change this saved. Excellent. So first, I want to interrupt the execution because something's happening, and then I want to run the cells that I just made. So this one just ran nicely. What's going on here? What's the error? No error. What's happening here? There's an error. That's because I don't have the colon, which is an easy thing to fix. Okay, and then this one certainly has an error with the naming. So what is it going to be? Invalid syntax. Yes, on the calling of a function, you in fact don't use the colon, which I failed to do in the opposite direction as well. Now what do we have here? Okay, did I not write down the get action function, or did I just write it down in camel case? I wrote it down in camel case, so that's an easy fix as well. And let's see what's going on here. Let's try to run this one more time and see what occurs. So here the name action is not defined. Yes, because we want to import the state, not the action, as the input of get action. Oh, it's reference before its time. Is that right? I don't think so, because it was initialized here. So 1 second. Local variable state referenced before assignment. Are these not the same two states? Hold on, let me rerun this. Can't believe what I'm saying. What? Oh, sorry, it's in this function where it's messing up in get action. Okay, I thought I was doing something wrong in there, which I wasn't. Oh, what's going on here? What's going on here with that capital letter state? You silly goose. Okay, so let's go ahead and write it down. Boom. Oh yeah, update policy is already working. Please no errors. Still errors. Can't multiply sequence. Okay, that's also true because I didn't index, I think. Hold on. Okay, GFT does not actually equal list equals 0. It's an actual number. What am I doing? Okay. Hopefully I don't have any other errors in here. Still. List object is not called. Indeed. So policy gradient is a list, but I just didn't put the append here at the in between those two. So let's see if we can get it now. Get it going. Oh no. Look available policy gradient also reference before assignment. Okay. Let's see what we did wrong here. Let's see what we did wrong here. This is reference before assignment. In the zip method. Okay, after negative log prod. Okay. In zip. So we append the product. We reset those to 0 nicely. Did I just spell something wrong? Oh my god. What am I doing with this camel case and mixing everything up? It's because I'm following a tutorial that uses underscore spacing, but I myself always use camel spacing. Okay, now what's the issue? Still. Oh, okay. Jesus, man. Just using it all over the place. This is a very good lesson for anybody watching to keep your naming conventions consistent. Okay. That's also true. Hold on, though. Policy gradient is a list. It's not a tensor. Wait, why didn't the zip work properly? Jesus, okay. Why did that space get there? Hopefully I won't get the same error this time, because I don't know how to solve it if I do. Okay. Why? Is policy gradient a tensor object, everybody? Policy gradient is initialized as an empty list. And then it's appended to, which seems legit. But apparently not. Let me go ahead and check my resource, which is on my phone, in order to see why this is not cooperating. So indeed, that is what I did in my own implementation. I appended. Let me just run everything once more, because I think there's something from the last function or something that's causing issues. So let's just run this. Or is it because I didn't run this? It's after I actually solved it, after I fixed the error. Let's see. Boom. Please. What? incredulous to this. I create a list. Hold on, guys. Interesting. Okay, I'm just going to keep on going until I get this solved. Sorry if it causes issues, but I don't know why I'm getting these issues. I'm really trying to think here. What's the issue? But I can't. Might have to ask ChatGPT. Why are you doing this, bro? It's a list. It's a Python list. If I went like this, because I know you can also do that. So I'm literally initializing it as a Python list, and you're still saying that it's a tensor object. I am absolutely shocked. Can't believe this. Okay, well, I'm basically gonna break the beans and tell you guys that literally that implementation is just above here. So if I look at the implementation, I need to see where I'm going wrong. It's literally the same thing. If I just literally copy paste this, what's going on here? Okay, now all of these are fucked up because I've changed the names of functions. Whoa, Jesus. That's weird, that's weird. Okay, well, I'm not going to finish this until I actually solve this issue. So let's see. Oh, is my... Hold on. Okay, that's good. Oh. Why am I doing this for the entire for loop? Oh my god, bro. Why am I so delusional? Why am I so delusional? I didn't unindent the for loop. Okay, whatever. Why am I getting a plot? Indeed, it's a Y label. Okay, let's keep on going. Oh, okay, and guys, you don't want to print this after each episode. That's just stupid. I mean, you can if you want, I guess. Okay, why am I printing a list? Okay, so cumulative rewards is... Oh, okay, I need to actually... Duh. This needs to be episode -1, guys. Come on, let's go. Let's get real here. Shout out to Gavin for saying that the first time. Anyways. Let's get real here and get this loaded up. Oh, did I spell episode wrong? Indeed, it should be episode -1. I don't know why I thought I had a list of a list. I mean, I didn't know why I thought episode was a list, because it's literally an integer. I don't want to run all, I just want to run this one. Please run. Okay, so let's go down here. So we got quite a few nice runs here. Got quite a few nice runs, and then it just didn't work. Oh, keyboard interrupt. Hold on, I didn't do a keyboard interrupt. Okay, there you go. So we're chilling now. And we're gonna see like how the learning is. Just going absolutely stupid. Like, look at this learning, bro. This learning is beautiful. I don't know why it's running so fast. I think Google just gave me like 5 times the resources as well. Boom. Oh, yo, check that out. That's absolutely beautiful. Jeez, guys. Yo, I think Google saw that I was recording this video and gave me like 10 times the GPU power, because this takes like 10 hours to train usually. Jesus. So, like I was saying, the trajectory of this video just completely flipped. It was like I was so dejected, but look at that bad boy. So, first of all, look at the noise of the actual return, the sum of the rewards over each episode, and the rewards over the last 10 episodes. First of all, you can see that at the very beginning, like the first 10 episodes, or like that at the very start there, it kind of is the same, because even though we're waiting over the last 10 episodes, when there's only 5 episodes, it's the sum of the last 5. But notice the general trend of the orange line. It is definitely strange and peculiar that the average rewards could have such a big drop, even so. But once more, I think that's just the fact that Vanilla Reinforce does have issues with its stability. And you can see in numerous occasions, probably especially in this one, it was due completely to random luck. We actually completed the episode, because once it hits 200 time steps, it just terminates, even if it's select rate. But you can see the occurrence of that greatly increases. And luckily, in our last episode, the 499th one, since episode 0 was the first one instead of episode 1, we actually also finished the episode completely. And once more, notice the completely monotonic trajectory in the upwards direction, which I myself foretold, even though it's not a crazy thing to predict. But yeah, that's all. I'm definitely going to be doing a tutorial on ActorCritic, and probably redoing this tutorial because it was not good whatsoever. I'm doing this more for myself than anybody else, but if somebody watches this and he gets 1 cent, 1 cent of 1 cent worth of help, then I'm content.